Imagine you are hunting for the best possible answer, and the landscape of answers looks like this: jagged, full of peaks and pits, with no smooth slope to slide down. There are millions of candidates, and no formula pointing you uphill. Ordinary hill climbing gets stuck fast. It creeps to the top of whatever bump it happens to be standing on and calls it a day, never seeing the far taller peak one valley over. So we borrow a trick from nature. Instead of one searcher, keep a whole population of candidate answers. Let the fitter ones breed, mix their parts, throw in an occasional random change, and generation after generation, the population as a whole climbs toward the best. That is a genetic algorithm. Everything starts with one idea. Turn a candidate solution into a string we can chop and splice. Borrowing the biology word, we call that string a chromosome. The simplest choice is a row of bits, zeros, and ones. Each bit is a gene, one small decision. Maybe a 1 means take this item, a 0 means leave it. Read the whole string, and you have decoded a complete candidate answer. The string is the genotype. The answer it stands for is the phenotype. A population is just a handful of these strings, a set of guesses, all alive at once. Here are 4 of them. Together, they are our starting generation, Generation 0, usually thrown down at random. A genetic algorithm repeats the same 5 moves over and over. Let me name them once. Then we'll watch a single round happen for real. First, fitness. Give every candidate a score for how good an answer it is. Higher is better. Second, selection. Choose which strings become parents, and bias that choice toward the fitter ones, so good genes get more chances to spread. Third, crossover. Take 2 parents, cut them at the same spot, and swap their tails to build 2 brand new children. Fourth, mutation. With a small chance, flip a random bit. This injects fresh variety, so the search never gets permanently stuck. And fifth, repeat. Those children form the next generation, and the whole cycle turns again. Round after round, the population's best fitness climbs. Here is our population of 4, and the fitness rule is deliberately simple. Count the 1 bits. More ones, higher fitness. The green bar beside each string shows its score. Read them off. C1 has 3 ones, fitness 3. C2, just 1. C3 has 4 ones, our fittest so far, fitness 4. And C4 2. The population's best right now is 4. Selection now picks 2 parents, favoring high fitness. The fittest, C3, is an easy pick. Alongside it, C3's neighbor C1 with fitness 3. These two will breed. Bring the 2 parents together. Parent 1, C3, 1 1, 1 0 1. Parent 2, C1, 1 0 1 1 0. Choose a crossover point, say, right after the second bit. That single cut line runs through both strings. Now the swap. Child 1 keeps parent 1's head, then takes parent 2's tail. Child 2 does the mirror image. Parent 2's head, parent 1's tail. 2 fresh candidates, each a blend of the 2 parents. Finally, mutation. With a small probability, flip 1 random bit. Say child 1's last bit flips from 0 to 1. Watch what that does. Child 1 becomes all ones, fitness 5, higher than either parent. Mutation just found something neither parent had. Let's slow down on selection, because it is where the pressure toward good answers comes from. The classic method is a roulette wheel. Each candidate gets a slice of the wheel proportional to its fitness. Same 4 candidates, with fitnesses 3, 1, 4, and 2. Add them up. The total fitness is 10. Each candidate's selection probability is simply its own fitness over that total. So C3, fitness 4, takes the biggest slice, a 40% chance. C1 gets 30%, C4 20, and poor C2, fitness 1, only 10. The wheel is spun, and wherever it lands, that candidate becomes a parent. Notice the balance. Fitter strings are far likelier to breed. So good genes spread. That's exploitation. But even the weakest keeps a small chance. So no candidate is ever thrown away for certain. That keeps exploration alive. A common alternative, tournament selection, picks a few at random and keeps the best of them, which is even simpler to run. Let's do one more crossover cleanly, start to finish, computing every fitness by hand. Two parents, 6 bits each. Parent 1, 110100. Parent 2, 011011. Their fitnesses first. Count the ones. Parent 1 has 3 ones. Parent 2 has 4. Now cut both after the third bit and swap the tails. Child 1 takes parent 1's head, 110, then parent 2's tail, 011, giving 110011. Count its ones. 4. Child 2 is the mirror, 011100, 3 ones, and a mutation to close. Flip child 1's fourth bit from 0 to 1. It becomes 110111. 5 ones, fitness 5. From two parents scoring 3 and 4, crossover, and a single flip produced a child scoring 5. That upward drift, repeated, is the whole engine. Here is why that random flip matters so much. Remember the trap from optimization. A searcher that only ever moves uphill gets pinned at the top of a local bump, unable to cross the valley to a taller peak. A hill climber sitting on the small left peak is stuck. Every nearby step looks like going downhill. But mutation makes a bold, random jump. It can fling a candidate clear across the gap, onto the slope of the far, taller peak, where selection then takes over and climbs. And here is the reward, plotted. On the horizontal axis, the generation number. On the vertical, the best fitness anywhere in the population. This is the curve you actually watch when a genetic algorithm runs. It starts low. The random generation 0 is mediocre. But each round, selection keeps the good. Crossover recombines it. Mutation adds the occasional leap. So the best fitness ratchets upward. 2, 3, 4, never falling. Because the best is always carried forward until it flattens at the top. Here, fitness 5. The Alvan string, the global best. The population has converged on the optimum. That rising then flattening curve is the signature of evolution doing its work. So when should you actually reach for this? Genetic algorithms shine exactly where calculus fails. When there's no gradient to follow, when the space of candidates is enormous and made of discrete choices, when the landscape is rugged with countless local peaks, and when a good answer found quickly beats a perfect one found never. But be honest about the costs. A genetic algorithm gives you no guarantee of the true optimum, only a decent answer. It has many knobs: population size, mutation rate, crossover rate, how you select. Every fitness evaluation can be expensive, and there are thousands of them. And if a real gradient exists, plain gradient descent is almost always faster. Don't reach for evolution out of habit. Your turn. Two parents, 4 bits each. T1 is 1011. T2 is 0110. Do a crossover cut after the second bit, and then compute both children's fitnesses. Remember, fitness is just the count of 1 bits. Pause here, work it through, then check against me. Here's the reveal. Keep the first 2 bits of each parent, swap the last 2. Child 1 is 10, then T2's tail 10. That's 1010. 2 ones, fitness 2. Child 2 is 01, then T1's tail 11. 0111, 3 ones, fitness 3. If you got fitness 2 and fitness 3, you have genuinely run a crossover by hand. That is the beating heart of the whole method. Trap 1. Premature convergence. If one lucky string takes over the whole population too fast, everything looks alike, and the search freezes on a mediocre answer. Fitness scaling and keeping some diversity are the usual cures. Trap 2. The mutation rate is a knife's edge. Flip bits too often, and you've destroyed all the good structure crossover built. You're just doing random search, but flip too rarely, and you lose the very escape hatch that gets you out of local traps. Too little mutation, and the population stalls. You have to tune it. Trap 3. Never claim the answer is optimal. A genetic algorithm returns a good solution, not a proven best one. If you need a guarantee, this is the wrong tool. And trap 4. The encoding is everything. If your bit string is designed so that splicing to good parents tends to make broken children, no amount of evolving will save you. Choose a representation where good parts combine into good wholes. Let's bring it home. A genetic algorithm encodes each candidate answer as a chromosome, a bit string, and keeps a whole population of them alive together. A fitness function scores every one of them for how good an answer it is. In our examples, that was simply the number of 1 bits. Selection chooses parents with a bias toward high fitness by roulette wheel or tournament. So good genes get more chances to spread. Crossover splices to parents at a cut point into children, and mutation flips the odd random bit, the jump that lets the search escape a local trap. Repeat that over many generations, and the population's best fitness climbs. It's the tool to reach for when the space is huge and rugged, and there's no gradient, as long as you can live without a guarantee of the very best.